Okay, let's look at this problem from our rotational equilibrium packet. This is number 7. We have a disk. We could think of it as being like a cylinder with a weight W that's at rest, and it's being supported by a cable right here to prevent it from slipping down the plane. And we want to find what the tension in that cable is, as well as finding the minimum coefficient of friction so that there's no slipping that occurs. In order to understand what's happening here, we first need to kind of think about all the forces that are acting on the system. So we're going to have a tension in this cable, which we'll call T. There's also going to be a contact force at the plane going straight through the center, which we'll call the normal force N. There'll be a weight pulling down from the center of the object if we say that it's a uniform disk. And finally, there's going to be a friction force that's going to point back up the ramp here to prevent the disk from slipping. And we'll call that one script F. All right, so the system is at rest, which means that it's in equilibrium. And if we want to find what the tension in the cable is, we can use two of our conditions for equilibrium. The first thing that we can note is that if we choose to look at the center of our disk right here and say that if we sum all of the torques acting about that point, so we're going to take this point right here to be our axis of rotation, then we note that the normal force points straight through that axis, so it produces no torque. The weight pulls down on that axis, so it produces no torque about that axis as well. So we're just left with F and T. The friction force is going to be at a right angle right here, and the tension, the cord is attached tangent to the top of the circle, so that's also going to be a right angle. This distance is the radius of the disk itself. So summing the torques, we're going to get the torque for this one's going to be T times this distance R. This one's going to be F times R. This one will be positive, let's say clockwise is positive, we'll get TR minus FR equal to 0, which means that T is equal to the friction force F, and we'll need this for what we'll do throughout this problem. Next, in order to actually find the value of the tension in terms of the weight W and the angle theta, it's helpful to draw a free body diagram that allows us to more easily see what the angles in the problem are. We'll start off by drawing a line here to represent our inclined plane. That's the plane that's inclined down here at an angle theta. And now redrawing each of these forces about the single point, we'll have normal force like this. We'll have the friction force up this way. We'll have the weight pointing straight down. And finally, we'll have the tension force pointing like this. Now, none of these are going to be to scale, but we're just doing this to find what the value of T is. Theta here is going to be the same as the angle theta here. However, what we're going to do for the first part to find the tension is we're going to define our xy axes so that this direction is the positive x direction. We're going to define this to be the positive y direction, up this way. That's going to be negative y direction. And we'll need to break up any of our forces into components. So for example, the weight W will break up by dropping a line down like that, and then a line over here perpendicular to that. And that'll give us components of our weight that are parallel to our axes. We'll define this angle also to be theta. You can figure out from some relationships with triangles that if this is theta, this should be 90 minus theta, and this then is also theta. We then define the length of this side to be W cos theta, this side to be W sine theta. And likewise, we can break up our tension force. In order to not clutter up the diagram too much, we will just state what that is as we calculate this. Now we only need one equation to find tension, it turns out, and that is the relationship that the sum of all forces in the x direction is equal to 0. Our x direction is along the plane, so F minus W sine theta plus the x component of our tension. So since this angle is theta, that's going to be t cos theta. And now we can solve this for the tension. Since we know F is equal to T, we end up getting that T plus T cos theta equals W sine theta. Factoring out our T, we get that T times 1 plus cos theta is equal to W sine theta. And then dividing the coefficient here, we get that T is equal to the weight times this fraction of sine theta divided by 1 plus cos theta. That's our tension. Next, what we want to find is the value of the coefficient of friction, the minimum coefficient of friction that we need, so that there's no slipping that occurs in the system. Now, we could use the sum of all forces in the y direction. However, we get a relationship that is algebraically just a little bit difficult to handle. So, to keep things somewhat simple, we're going to draw the same free body diagram, but we're going to choose a different set of xy coordinates. So again, we draw all of our forces as we did before. There's our object. There's W, the weight, F, the friction, N, and the tension. And now what we'll do is we're going to choose this direction to be the positive x direction, and we'll choose this direction to be the positive y direction. Now, again, we'll label our angles. This angle is going to end up being theta. That angle is going to end up being theta. And if we sum the forces in the x direction again, what we'll have is F multiplied by the cosine of theta to get a component here. Oops. F cos theta plus T minus the component here of N, which will end up being across here. Here, this one, if this is N sine theta. So we get minus N sine theta. And what we can do now, oh, and this is equal to 0. Now we can use the fact that the tension T was equal to the friction force and say what we have here is F times cos theta plus 1, T is the same as F, is equal to N sine theta. And then what we can do is to take the ratio of the friction force divided by the normal force. That should be equal to the coefficient of friction, which is going to be equal to sine theta over 1 plus cos theta, and that's our answer. Turns out to be the same fraction that appears in this